Hello all. Today in this session we are going to discuss about fundamentals of digital circuits. Before we actually go into fundamentals of digital circuits, I would like to quickly recap on the fundamentals that we have discussed in analog electronics. Once we differentiate between analog electronics and digital electronics, we will actually step into the fundamental concepts of digital electronics. So, the quick recap of analog electronics are summarized into this following points. So firstly, we have seen that analog electronic deals with continuous signals, right? So we have started with diodes and then we have started with transistors, where we have discussed briefly about bipolar junction transistors, and we also discussed about field effect transistors. So we have seen that all these analog electronics deal with continuous signals that vary smoothly over time. And apart from that, we have also seen that analog signals can take, or analog electronics which deals with continuous signals take any values within a given range. This was the first thing that we have discussed in analog electronics. And coming for the representation, we have seen that all the analog electronic circuits are represented by continuously varying voltages or currents. And we have also seen that analog signals can be represented by infinite number of values. Apart from the representation, we have also seen that analog signals are very sensitive to the variations and require high precision components for accurate processing of the signals. So when we talk about the signal processing, we have also seen that analog electronics perform some of the basic signal processing applications like amplification, filtering, modulation, etc. on the continuous analog signals. We have also seen that analog signals are susceptible to noise and any interference that can degrade the quality of the signals. And at last, we have also seen various applications of analog electronics which are basically used in audio systems, RF radio frequency circuits, analog sensors, and other applications where the continuous signal processing is actually used. So now when we discuss about digital electronics, okay, when I want to explain about the digital electronics, the fundamental thing that I would like to focus is about the discrete signals. While we have looked into analog electronics, we have seen that they process continuous signals, right? Now when we discuss about digital electronics, this digital electronic deals with discrete signals that have specific distinct values, okay? Unlike analog electronics where it can take value within any given range, digital signals have discrete values within a specified range, usually represented by the binary digits 0 and 1. This is the first and fundamental concept that you have to understand when we discuss digital electronics. Next, coming for the representation, usually the digital signals are represented in various forms. When you are using the binary code, they are usually represented with 0 and 1. We also have other forms of representation of the digital signals, which we will see once we step into the concepts. Now, when we talk about precision, okay, we have seen in analog electronics, we have seen that analog electronics are sensitive to small variations, right? Unlike this, digital electronics can tolerate, this is the major advantage, digital electronics can tolerate a certain level of noise without affecting the integrity of the information being processed. Now coming for signal processing applications, digital logic performs various operations using logic gates. So this is the major focus for today's class. So we will be discussing, once we are done with the fundamental concept of digital electronics, we will be looking into what are these logic gates and other digital components to process these discrete signals, okay. Now after we look into the basic concepts of digital electronics, we will also see how do we perform some basic logical and arithmetical operations on these binary codes. Now when we talk about noise immunity, digital signals are less susceptible to noise unlike analog signals, okay. And we also have various error correction techniques that are employed with digital signal processing. Apart from that, when we look into the application areas, digital electronics are relevant in computers, microcontrollers, digital signal processors, communication systems, satellite communications. So whatever the communication related aspects we look into, the computer related communication aspects, we majorly use digital electronics. So in order to summarize them, so I have this summary of few points that I have put up together for you to differentiate between analog and digital electronics. So first thing, that is all about nature of signals. So as discussed, analog electronics deals with continuous signals with infinite possible values, whereas digital signal deals with discrete signals with distinct values, most probably the binary digits. When coming for representation, analog electronics are represented with voltage or current levels, whereas digital electronics are represented with the binary code zeros and ones. So when we discuss about precision and sensitivity, analog electronic requires high precision and they are sensitive to small variations of currents or voltage, whereas digital electronics tolerates certain level of noise and can be more robust. Processing methods, these process continuous signals. Digital electronic process digital signals using logic gates and other digital components, which we are going to discuss today in the class. So we have seen various applications like audio systems, RF circuits and analog sensors for analog. When it comes to digital, we have seen communication systems, the computers that we use and the microcontrollers. Okay. So to begin with digital electronics. Okay, so I would like to discuss about what digital electronics is all about. Okay, so digital electronics is a field of electronics where it involves study of digital signals. Okay, so the binary representation of digital signals 0 and 1, how are they studied, how are they processed, is all about your digital electronics. So these are made from large assemblies of logic gates often packed in integrated circuit. Okay, so before we actually go into logic gates and integrated circuits, I would like to tell you the basic concepts of digital electronics in terms of zeros and ones. Okay, now this is the first diagram that you see here is an analog signal. So as we can see, it is a continuous signals, right? So there is no particular fixed value for this analog signal. So the physical quantities or signals may vary continuously within a given range. That is an analog signal. On the right hand side, you can see a digital signals wherein the physical quantities or the signals or the information that we give can assume only discrete values. There is no continuity. All the values within the specific range are discrete. Okay. Now, a basic binary digital signal. As I told you, the binary values are represented in different ways, and the first and foremost basic way is 0 and 1 representation, right? Apart from this, you can also represent the digital signals with words. You can give false or true. You can also represent low and high. You can also use the words on and off. Okay, so usually we represent 0 for false, low or off, and 1 for true, high and on. These are the various representations which we use for representing our digital signals. Okay. Now when you look into this particular figure, this is the binary digital signal. 0 and 1 is represented as a digital signal in this way. Okay. So basically binary values are represented by some range of values of the physical quantities. Okay. Now when we talk about digital electronic circuit, we have talked about binary signal, right? 0 or 1, low or high, true or false, on and off. Okay, that is a binary signal. So when we talk about binary signals, we also have to look into what digital electronic circuit is all about. Okay, so the basic digital electronic circuit has some inputs and outputs. Okay, now the input and output, both of them again will be in the binary representation, but before we go into that, we will see that the digital electronic circuits operate with voltages of two logic levels. Basically we call them as logic low and logic high, or usually we represent it with 0 or 1. Okay, now as discussed, the basic digital electronic circuit has one or more inputs and gives you a single output, which is known as a logic gate. So logic gate is the basic digital electronic circuit which accepts the input and produces the output. Okay, so the logic gates. So when I talk about this logic gates, these logic gates are the building blocks of any digital circuit. So if you want to design any digital logic circuit, we will have to look into the logic gates. What are these logic gates? How many types of logic gates are there? And what is the symbol of the logic gates? Okay. So when we talk about logic gates, we categorize them into three different types. Okay. The first one is the basic gates, second one is the universal gates, and third one is the special gates. So basic gates, universal gates, and special gates. We'll look into the first category of logic gates. Okay. So first and foremost category of logic gates is basic logic gates, and there are three types of basic logic gates. First one is your AND gate, OR gate, and NOT gate. Okay. So we start with NOT gate first, and then we will go with AND and OR. Okay. So this is the first basic digital logic gate, which is called as NOT gate. Okay. Now when I explain you about each and every logic gate, I'll give you the definition of that, the functionality of it. Along with that, we will also look into the symbol and the truth table. All of you must know what truth table is all about, right? The functionality of the logic gate with representation of zeros and ones are represented in your truth table. Okay. So the simplest form of digital logic circuit is the first gate, which is called as NOT gate. Now NOT gate consists of only one input. As we can see here in the symbolic representations, we have two different symbolic representations, out of which the first one is most probably used. Okay. So as we can see here, A is the input here. We have only single representation of input A, out of which the NOT gate performs the complement operation. Okay. The NOT gate performs complement operation or inversion. So when I take A as input for this NOT gate, the output of that particular gate will be A complement. We call this as A inversion, or we usually call it as A complement. Okay. Now when we look into this truth table, here is my A input, here is my Y output, which is not A or A complement. When I take 0 as input, my output will be 1. When I take 1 as input, my output will be 0. So the complement of the input is done by your NOT gate. So basically, NOT gate performs inversion operation. Okay. Now the second logic gate is AND gate. Okay. AND gate is a logic circuit that has two or more inputs. I can take in the diagram here, I have taken two inputs, A and B. You can also take three inputs wherein A, B, C, or you can take n number of inputs. Okay. So basically AND gate is a digital logic circuit which can take two inputs and performs multiplication operation. This is called as AND operation or multiplication operation. Okay. Now when we look into the operation of the gate is such that, see, what does AND operation do? When we discuss about this AND gate operation, we are taking two inputs here, A and B. So when I take binary representation of two inputs, I have four combinations, 0, 0, 0, 1, 1, 0 and 1, 1, right? So when I take two inputs, I have these four combinations, 0, 0, 0, 1, 1, 0 and 1, 1. The binary representation of this is 0, 1, 2 and 3. Okay. Now this is something like this. Okay. So when I talk about binary representation of 0 and 1 as 2 bits, A and B, I write them as 0, 0, which is the corresponding 0th number, and then I write 1 as 0, 1, and then I write 2 as 1, 0, and I write 3 as 1 and 1. Okay. So when I take 2 bits, these are the 4 combinations that I generate from those 2 bits, 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So that is what I am representing here in the truth table in the input columns. Okay. 0, 0, 0, 1, 1, 0 and 1, 1. Now when we look after the output part, when you take A and B as inputs for the AND gate, the output is A into B. Okay. So 0 into 0 is 0. 0 into 1, 0, 1 into 0 is 0, 1 into 1 is 1. That is, the operation of the gate is such that the output of the gate is 1. Here the output of the gate is 1 only if all the inputs are 1. Even if one input is 0, the output will be 0. I repeat, the output will be 1 only if all the inputs are 1. the output will be 0 even if one input is 0 because I am performing multiplication operation, and this is the logic symbol of AND gate. Next we look into OR gate. Okay, now this is the logic symbol of OR gate. We have curved here. Okay, instead of straight line that we have seen in the AND gate, we have curved line here in the input side. Okay, similar to AND gate, OR gate also can take 2 inputs or more than 2 inputs, and coming for the output operation, it performs addition. Okay, AND gate performs multiplication operation, whereas OR gate performs addition. Okay, so now when we look into the truth table of this, the same thing, as we have taken 2 inputs, we have 4 different combinations of these 2 inputs, 0 0, 0 1, 1 0 and 1 1. As I am performing addition operation here, the operation of OR gate goes on like this. Okay, the operation of OR gate is such that the output is 1. The output is 1 if one input is 1. If any of the input is 1 or if both the inputs are 1, the output will be 1, and the output is 0 when all the inputs are zeros. Okay, I repeat. The operation of OR gate is such, the output is 1 even if one input is 1, and the output is 0 if all the inputs are 0. So this is the truth table and this is the logic symbol and the definition of the OR gate. Okay, so these are the 3 basic gates. The first one is NOT gate, second one is AND gate, and the third one is your OR gate. Okay, now we'll go to the next category, which are called as universal gates. Okay, so first classification is, we have seen NOT gate, second we have seen AND gate. NOT gate performs, if I take A as input, my output will be, if I take A as input, my output will be A complement, and in AND gate, if I take A and B as inputs, my output will be A into B. And third category, OR gate, where if I take A and B as inputs, my output will be A plus B. Okay, so these 3 are the first category that comes under the basic gates. Okay, now we will look into the second category of gates, which are called as universal gates. We will look into the second category, which are called as universal gates. Okay, now we have these 2 gates which are called as NAND and NOR. NAND and NOR are called as universal gates. I will tell you why do we call them as universal gates once we complete with the basics. Okay, NAND and NOR gates are called universal gates because we can implement any Boolean function using only NAND and NOR. Okay, as I told you, first let's discuss about what is NAND and NOR, and after I explain you about NAND and NOR, I will tell you why are they called as universal gates. Okay, now the term, as we see here, the term NAND is a contraction of the expression NOT and AND gate. As you can see, this is the logic symbol of NAND gate. Okay, so this is the logic symbol of NAND gate, where we can see this is contraction or addition of AND gate along with the inverter, hence the name NAND gate. And as you can see, it is AND operation with complement. That is the reason it is called as NAND gate. NOT with AND is called as NAND gate. So this is the brief elaboration of the logic gate. So that we have AND gate, which produces A into B, which is connected to inverter, which produces A into B complement, which is the algebraic output expression of NAND gate. Okay, now when we look into this particular truth table, as you can see, so NAND gate operation is something like this. Okay, as you can see, NAND gate produces logic output 0 when both the inputs are 1, and NAND gate produces logic output 1 even if one input is 0. Okay, so this is the truth table for NAND gate, which is nothing but complement of your AND gate. Now when we look into this NOR gate, okay, so as the name itself says, it is combination of what? OR gate and inverter. So OR gate output was A plus B, which is connected to an inverter which produces A plus B whole complement. So the truth table is exactly the opposite of your OR gate. Okay, so the output will be 1 if both the inputs are 0. In rest of the cases, my output will be 0. So this is your NOR gate. Okay, so far we have discussed about the basic gates NAND, not and or, and also the two universal gates which are NAND and NOR. Okay. Now the last category of gates which are called as special gates. The third category which is called as special gates, and we have two special gates. One is called as exclusive OR XOR, and the second one is called as exclusive NOR or XNOR. Okay. Now let's look into what are these. These XOR and XNOR gates are called as special gates because these two gates are special cases of OR and NOR. Okay. Now when we look into this particular symbol, this is bit different. Okay. So we have this encircled plus symbol to represent our XOR gate. Okay. Please make a note of this. A encircled plus symbol is representing our XOR. So this is A XOR B. Okay. So the exclusive OR gate returns high output. This is your logic symbol and this is the truth table. Let us focus on the truth table. Okay. Now this returns high output with one or two high inputs. Okay. So when you have both the inputs as different, okay, when you have both the inputs as different, you will be getting high outputs. That is, when you have both the inputs complementing each other, we will have high output. When you have both the inputs as same, we will be getting zero output. Okay. When we talk about this encircled plus symbol, that is nothing but A complement B plus AB complement. Please make a note of this formula. XOR gate is all about when you are taking XORing the two inputs A and B, it is nothing but A bar B plus AB bar. Okay. So it is something like this. XOR gate, the logic symbol for XOR gate is encircle plus symbol, and when you take these two inputs, the output Y will be A complement B plus AB complement. When you are applying zeros and ones here, we will be getting that particular truth table. Let us take one case. If I take A and B as 0, 0. Okay. Now when I apply the same here, I will be getting, when you take A as 0 and B as 0, A complement is 1 into 0 plus 0 into 1. That is 0 plus 0. That is equal to 0. Okay. So when you are taking both the inputs as same, you will be getting the output as 0. Okay. Now let me take A is equal to 0 and B is equal to 1. Let me apply the same here. Now Y will be A bar B plus AB bar. So when I apply this, 0 complement will be 1 into 1 plus 0 into 0. That is 1. So when I am taking two different inputs, I am getting high output. When I am taking two same inputs, I will be getting 0 output. Okay. So now understand, when you are taking both the inputs as same, the output will be 0. When you are taking the complement of the inputs, the output will be 1. This is your XOR gate. Okay. And the last gate is the XNOR gate. Okay. Now the XNOR gate is complement of XOR gate again. Okay. As you can see, we are adding. When you look back, I don't have inversion symbol here, right? I am taking one OR gate upon which I am applying my XOR operation. But when you look at this exclusive NOR, this is nothing but adding inversion to the XOR gate. Okay. So there are two variations you can apply. You can represent your XNOR gate. You can represent your XNOR gate in two ways. One thing is A XOR B whole complement, or you can also write it as A XNOR B. Okay. Encircle dot symbol or encircle plus complement will give you your XNOR gate. Okay. Now when you look into the truth table, when we focus on the truth table here, the complement of XOR is XNOR, right? So the operation is different here. Okay. So when you look into the first case, when both the inputs are same, and the last case, when both the inputs are same, that is 0, 0 or 1, 1, the output will be high. And the next two cases, when both the inputs are complementing, the output will be 0. Did you all get this? So in the previous case, when the inputs are complementing, the output is high for XOR. But when you go for XNOR, when the inputs are complementing, the output will be 0. And how did we get that? When you apply zeros and ones in the given equations, that is A bar B plus AB bar. And when we talk about XNOR gates, Okay, when we talk about XNOR gate, we have this expression y is equal to a into b plus a bar b bar. Okay, here it is a bar b plus a b bar, whereas for XNOR we have a b plus a bar b bar. This is all about the logic gates. So we have seen 7 different types of logic gates, starting with NOT gate, which performs inversion operation, AND gate, which performs multiplication, OR gates, which performs addition, NAND gate, which performs complement of AND operation, NOR gate, which performs complement of OR operation, XOR exclusive OR operation, XNOR exclusive NOR operation or complement of your OR XOR operations. Okay, so these are the 7 logic gates which are the basic building blocks of any digital circuits. If you understand all these logic gates along with their symbols, their functionality and truth tables, you can design any digital logic circuit. Okay, now before we actually step in further, I want to focus on the universal gates. Okay, so what are universal gates? We have discussed that NAND and NOR are called as the universal gates, right? Now I will tell you why are they called as universal gates, right? Now we have these 3 basic gates, right? AND gate, OR gate, NOT gate. If suppose I want to perform addition operation, I have to go for OR gate. If I want to perform multiplication operation, I have to go for NAND gate. That is, there are 2 different types of gates or symbols that I am using. But in cases when you go for larger circuits, we want to reduce the number of logic gates being used. So I take only one gate and I want to design other gates using them. Okay, so NAND and NOR are called universal gates because any logic circuit can be designed by using only NAND and NOR. Okay, I know it is a bit confusing. Let us see why are they called so. Okay, now let's look into this. Okay, now what do you understand from this figure? What did we do in this first figure, guys? Please understand. I am taking only one input here called A. Actually, NAND gate should have 2 or more inputs, right? So what am I doing? I want inversion operation. I want inverter to be designed from NAND gate. So what am I doing? I am taking only one input and I am connecting 2 inputs to the NAND gate. Okay, I am taking only one input, I am shorting those inputs to the NAND gate. So when I do that, what will happen? What does NAND gate do? A into B bar. But I don't have any B here, but I have only A as repeated twice, right? So what will happen here? When you look into this is my NAND gate, right? This is my NAND gate wherein I have 2 inputs, A and B. Okay, but I want to design inverter from this NAND gate. So when we looked into inverter, it has only one input and it produces the complement of that particular input. So what I am doing is, in order to get your inverter operation, I remove this second input and I connect this input to the other input terminal. Okay, now what is output of NAND gate? Y is equal to AB bar, but here A is nothing but A itself. Okay, so we have a Boolean law, A into A is equal to A. So the output here is A bar. So when I am taking A as input, my output is A bar. That is, the inverter operation is being carried out. So in order to design NOT gate using NAND gate, what do we do, guys? We simply short 2 inputs together. This is the circuit. So that is, we proved that NAND gate can also be used to design what? NOT gate, by shorting the 2 inputs together and giving only one variable. Okay. Next, we will see NOT gate as AND gate. Now what is my next target? I want to design AND gate by using only NAND gates. Okay, now as you can see, I have taken 2 NAND gates. Okay, now when you look into this circuit, first I'll take one NAND gate. Okay, I'll give 2 inputs A and B, and the output of this circuit will be AB bar. Right, now what I want to do, I want to design AND gate from NAND gate. So what I do is, I short circuit this and give it to another NAND gate. So what will happen? This will be A into B bar into A into B bar, whole bar. This is A into A, which is again A. So we have A, B whole bar and whole bar, which is equal to A into B. Okay. So we are getting AND operation using NAND gate. Okay. Now look into the third operation. I want to design OR gate. I want to design what? OR gate. So what do I do? Look at this. I have taken 3 NAND gates here. First NAND gate shorted, the output will be A bar, like what we have seen. Second NAND gate, B input, shorted, B bar. Now these A bar and B bar I am giving it to another NAND gate, wherein I get my output as A plus B. So I can design OR gate using NAND. I can design AND gate using NAND. I can design inverter also using NAND. So basically any logic circuit can be designed by using only NAND gates. Okay. Next. Similarly NOR gates. Okay. So this is how we do. Shorting 2 inputs, that will give you NOT gate. Shorting one input to one OR gate, another input to another NOR gate, and giving together, we will be getting AND gate. This is reverse. Okay. That is addition operation. This is addition operation, that is multiplication, right? So this is how we get AND operation using NOR. This is how we get OR operation using NOR. Okay. So in short, the conclusion here is NAND and NOR are called universal gates because the basic gates or any other gates can be designed by using only NAND and only NOR. Okay. Now you may ask the question, Ma'am, when all the logic gates are available, why do we need only one logic gate for representing all gates, and what is the importance of these universal gates? Okay. Now if I want to design, see, first let me tell you about how are these logic gates available. Okay. These logic gates are available inside an integrated circuit. Okay. So one integrated circuit may have 4 or 5 logic gates inside it. Okay. So I have something like this. I have an integrated circuit like this, and I have one NOT gate, second NOT gate, third NOT gate, and fourth NOT gate. That is, this integrated circuits has 4 NOT gates. Similarly, I have another integrated circuits with 4 AND gates. Okay. Similarly, I have another integrated circuit with 4 OR gates. Okay. Now, when I want to design a digital circuit, with all these combinations. Okay. Now, what do? I need one IC of AND, one IC of inverter, and one IC of OR. So altogether I am using 3 ICs with which the size of the circuit will be more. But if I have all these operations using NAND, okay, then I will check only one NAND gate, okay, wherein I have 4 NAND, one IC which has 4 NAND gates. So instead of using 3 different ICs for designing my logic circuit, I will use only one IC because NAND and NOR are used as universal gates with which we can design any logic gate. So when you are designing digital, see, all these days we are getting very narrow, slim and complicated, compact electronic devices, right? Because we are reducing the number of components being used, and this is how the basic level of decreasing the more number of components. When you take individual gates, when you want to design a digital circuit, you have to use many different ICs. But if you are using all the digital logic gates using NAND and NOR, we may need only one integrated circuit. That is the reason we will use in universal gates which are NAND and NOR. Okay, focus on this once again. So these are NAND gate implementation of inverter and OR. Using only NAND gates, I am implementing inverter, I am implementing AND gate, I am implementing OR gate. So here only using NOR, I am implementing inverter, AND gate and OR gate. So that is the reason these are called as universal logic gates. Okay, now application of logic gates. Where do we actually use these logic gates? As I told you, the logic gates are building blocks of any digital electronic circuit. Okay, so when we talk about nanotechnology, medicine, multiplexers, adders, multipliers, many types of combinational and sequential logic circuits that we are going to discuss in the subject further requires the basic logic gates. Okay, now with this we are done with the basic logic gates concept. Okay, now once we are done with this basic logic gates, I would like to give you the basic introduction to Boolean algebra. Okay, so all of us know Boolean algebra is a mathematical structure which has set of operations, right? So we know the basic concepts of Boolean algebra, right? Now today in the class we'll look into how do we use this Boolean algebra for digital circuits. Okay, so we know that Boolean algebra was introduced by mathematician and logician George Boole in mid-19th century. Okay, and this stands as the basic for digital logic design or analysis of digital logic circuits. Okay, now there are various operations that we use in Boolean algebra, but there are three important basic operations. If you want to design any digital logic circuit, we need three important or basic operations, which are negation or not operation that we have already seen, and conjunction, which we usually study in Boolean algebra, which is called as AND operation here in digital circuits, and disjunction, which we have already seen in Boolean algebra, which is called as OR operation in digital circuits. So basically it is inverter, AND gate and OR gate. Okay, now before we actually step into the depth concepts of Boolean algebra, I would like to explain you the basic terminology of Boolean algebra. So often we come across these terms: Boolean algebra, Boolean variables, Boolean function, literals, complements and truth table. Okay, so I'll give you a quick recap on each one of them. Okay, so the branch of algebra that deals with binary or logical operations. Okay, so in Boolean algebra, when you're dealing with logical operations, we call it as Boolean algebra. Okay, now the variables 0 and 1, the variables that we are assigning the values 0 and 1 are called as Boolean variables. Okay, so basically we use these variables to store these values 0 and 1s. And then we have this Boolean function. Okay, so in short, if you want me to represent this, I would like to represent it this way. Okay, so we have this binary values 0 and 1. So if I am assigning A is equal to 0, B is equal to 1, this A and B are variables. Okay, now when I want to take a Boolean function, I take it as A into B. Okay, so I am forming this Boolean function with respect to this Boolean variables. Okay, so Boolean variables along with these operators, this is the operator that I am using. Okay, let me take another function, let's say A complement B plus AB. Okay, so this is a Boolean function which is a combination of the Boolean variables along with the Boolean operators. Okay, so the function of Boolean algebra that is formed by the use of Boolean variables and Boolean operators is called as Boolean function. Okay, literal. And Boolean algebra, n value. Okay, so this individual variable inside the function is called as the literal. Okay, now when you talk about this particular equation here, I have A complement B plus AB. So the negation operation for the individual literal is called as the complement. Okay, so the inverse of the Boolean variable is called the complement of that particular variable. The complement of 0 is 1 and the complement of 1 is 0, which is represented by over the variable. Okay, now truth table, we know the table consisting of all possible values of the logic variables, which has rows representing the inputs and outputs of each operation, is called as your truth table. Okay, now we will look into some basic identities. All of us know this, we have already studied them earlier. Okay, so we will just have quick recap or brush up of the basic identities of Boolean algebra. Okay, so these are the 9 basic, these are 17 basics altogether, which we have classified into 2 classes, 9 into relationship between single variable. Okay, so as you can see, the first 9 represents the operations on single variable x. I don't have y here, okay, x with different operations, whereas the second table, second half, wherein 10 to 17 are with two different variables, okay. So x plus 0, when you are adding 0 to one variable x, that will be x. X plus 1 is equal to 1. Please make a note of this, okay. X plus x is equal to x. X plus x complement is equal to 1. Okay, variable added with the complement of that variable will result to output 1. Okay, this is double complement. X double complement is equal to x again. See, x single complement is x bar, the negation. If you apply the complement again, it would be the original one. Okay, so x double complement is equal to x. Next, x into 1 is equal to x. X into 0 is 0. X into x is x. X into x complement would be 0. Okay, you can apply zeros and ones and you can check this. Okay, so the first half says the relation between a single variable x and the complement of x and the binary constants. Okay, x with binary constants, x with the same variable x on different operations. Okay, now when you look into the second half of this particular table, you can see two different variables, right? X with y or x with y and z and different operations. Okay, so x plus y is equal to y plus x. X into y is equal to y into x. X plus of y plus z is equal to x plus y of plus z. Similarly, we have this multiplication, and similarly x of y plus z is equal to xy plus xz. Similarly, we have this operation, and then we have this De Morgan's law, which I will explain you in brief the later. Okay, so when you are dealing with one variable with constant 0 and 1 and same variable, these are basic identities. When you are dealing with multiple variables, we will be associated with some Boolean algebraic laws. Okay, so these are some basic laws of Boolean algebra that I want to focus today, and we have the first law, which is called as identity law. Okay, identity law in two forms. We are going to discuss all these basic laws of Boolean algebra in two forms. One is OR form and form. So that is what we have discussed here. Okay, same AND form and OR form. This is your OR form and this is your AND form. Okay, so the same thing I am going to discuss with respect to the law name. Okay, so first we have identity law, which says p plus 0 is equal to p into 1 is equal to p. Okay, identity law. Next we have idempotent law, p plus p, identity, same thing, p plus p is equal to p into p is equal to p. We have commutative law, we have associative law, distributive law, inversion law and De Morgan's law. Okay, so the same table, the second half of the table is put into as basic laws of Boolean algebra. So here we call them as, the first half we call them as identities, and the second one we call them as laws of Boolean algebra. Okay, now identity law you can apply, and this is commutative law explained in detail. Okay, so we can have both AND and OR operation for each and every law. We have associative law, we have distributive law, inversion law and OR laws. Okay, now I would like to discuss about this important algebraic Boolean algebra theorem, which is called as De Morgan's theorem. Okay, there are two different laws in De Morgan's theorem which we are going to discuss now. Okay, now look at this. The first De Morgan's law says the complement of the product. Okay, you please look into the board. The most important law of all the Boolean algebra is the De Morgan's law. So we will discuss this particular thing today. Okay, now it says P into Q whole complement, the product of two variables. The complement of the product of two variables is equal to the sum of individual complements. Please make a note of this. The complement of product of two variables is equal to sum of complement of individual variables. That is, when you are dividing this complement in between two variables, when you want to separate this complement for two variables, your AND operation will become your OR operation. This is the first De Morgan's law. Focus on the board there. The complement of the product, P and Q is the product here, this is the complement. The complement of the product is equal to the sum of the complement of each Boolean variable. Did you get my point? So this is the truth table for the same. If I take P and Q as two different variables 0, 0, 0, 1, 1, 0 and 1, 1, this is my truth table. This is my first De Morgan's law. Okay. Now the second De Morgan's law says, this is the first De Morgan's law. Okay. Now the second De Morgan's law says, the complement of the sum variable, the complement of the sum variable is equal to the product of the complements of individual variables. The complement of the sum variables is equal to the product of complement of individual variables. So this is De Morgan's law 1 and this is De Morgan's law 2. Focus on the board. Look at this. The complement of sum of the two Boolean variables P and Q, P plus Q, is equal to the product of individual complements of P and Q, that is P bar plus Q bar, and this is the corresponding truth table of that particular De Morgan's law. So in today's class we have discussed about how are digital circuits different from analog circuits, and what is digital logic, what are digital circuits, what are logic gates. We have seen three different types of logic gates, which are basic logic gates, universal gates and special gates. And or not are the basic logic gates, NAND and NOR are the universal gates, XOR and XNOR are the special gates. Once we are done with that, we have also seen that any digital electronic circuit is designed by using the basic logic gates. Okay. So if you want to design the digital electronic circuits, we also have to understand some basic concepts of Boolean algebra. So we have seen what is Boolean algebra, some terminology related to Boolean algebra, and then we have also seen the basic identities, laws of Boolean algebra. In the next class, we are going to study about how do we design the digital logic circuits with the basic concepts that we have studied today. Thank you.